Since the idea, as I probably already said, since the idea of this course is to give you the principle of operation of optical instrumentation, it's not, in our opinion, important to go with too much difficulties in the exercises. Okay, so the idea is, okay, laser Doppler velocimeter. What is the most important thing to remember of such an instrument? The most important thing to remember is that. Let's go abruptly. Okay. And we need to remember that we start from a laser, the usual Hemi laser, for example. Then we have a beam. We can divide the beam into two equal sub-beam, let's say. Okay, quite correct. Then we have a lens. So we have two beams. These two beams are focalized in one spot of the space. So we have something like this. Okay, this is more or less correct. This is the optical axis of the system. Okay, and this is an angle theta. So what we know? We know that in the overlapping zone of the two beams, we have fringes of interference. Okay? So for example, let's suppose that we have light on the optical axis, then we have another fringes here, another fringes here, and so on the back. Okay? And the most important thing to remember is this distance d, or the distance between fringes. Okay? And in particular, this is given by the wavelength of emission divided by the sin function of the angle theta. Okay? Now, what is the principle? Now, let's suppose that here we have a liquid or a fluid that is moving. What we do, we insert particles in this fluid. So, for example, these are moving with a velocity in this direction. Okay. Now, when they find the, let's say, fringes zone, what we have that the light is scattered, okay, from the zone in which we have the maximum of light. Okay. And then, if we look at the scattered light or diffused light onto an oscilloscope, and we look at the frequency of peak, we can measure the velocity. Because what we know that the frequency that is related to velocity v is always given by the velocity of the particle divided by the distance d. Is this true? Is it true? Yes, it's true. Okay. So these are the most important things to remember for a laser Doppler velocimeter. Okay? So let's do our job. In particular, what we know? We know that this quantity is, or this distance, L is equal to 10 centimeters. Then we know that the Hemi laser is a 20 milliwatt, has 20 milliwatt of power, or emit on 20 milliwatt of power. The diameter of the particle is equal to 5 micrometer. Then if we start with 20 milliwatt, we have 10 milliwatt here and 10 milliwatt here, so these two fields have the same power. And now the beam waste of the two beams here in the overlapping zone is 5 millimeters. Okay? Of course, this is not a real situation. We have more fringes than this. Okay? So just to give you an idea. Okay. Now, first thing, what is the beam divergence from here in the far field? Because of course, here I have used the parallel line, but the reality is that when we are in the focal plane, we have something like this. Let's say this is the section of the beam, okay? So here we have the beam waist, and then the beam, when we move from the beam waist, is larger, okay? The question is, what is this angle? Let's call it alpha, okay? Well, this is not difficult. I mean, this is not related to the laser Doppler velocimeter. This is true in general. Alpha is always given by the wavelength divided by pi multiplied by the dimension of the beam waist. Remember always that the beam waist is the radius of the beam, okay? And in particular, this is given by 40 microradian. Okay? Okay. Second point. Now, okay. Given the particle diameter of 5 micrometer, we want to design the interference fringes with a fringe spacing equal to 10 micrometers. So, we want to build up an instrument that has a D that is equal to 10 micrometer, okay? So what does it really mean we want to build up an instrument that has this quantity? Means that we need to find out what is the angle theta, okay? So let's go on here. And, okay, what does it mean? That we have that sin theta is equal to lambda over 2 divided by d, and this means that theta is the arc sin of lambda over 2 divided by d. Okay? And of course the wavelength, this is a Heaney laser, you should know the wavelength. And so what we get 32.5 milliradian. Okay, the text says that he wants the result in degree. Okay, so you have to do the translation, and in particular, this is equal to 1.8 degree, more or less. Okay? And the question is a bit different because it asks what is the incidence angle of the tube beam. So the incidence angle is this one. Okay, so don't forget to say that beta, that is the angle that you have to find out, is equal to 2 theta, and so it is 3.6 degrees. Okay? And pay attention to this question. So don't forget factor of 2 somewhere during your exams. Okay? So pay attention on what the exercise asks. Okay? Because of course, if you go here, this is not wrong, but it's not complete. Okay. As I said, the exercises are not difficult, but you have to pay attention to trick, let's say. Okay. And another point, the exercise asks to evaluate the spot dimension WT of the laser beam at the inner surface of the pipe. So this is the pipe in which we have the fluid. And the point is, what is the dimension of the laser here? Okay, at this point. Remember, here we have that this quantity is W0, okay? And the question is, okay, what is, now let's try to have a more real picture. You will have something like this, okay? And so, what is the dimension of the laser here? Okay, so this is the question. If we work here, what we can say? We have to find out what is this distance. So let's call it L first, okay? Because we are moving from the position in which we have the beam waist, we are moving of a quantity, and then we want to find out what is the dimension of the beam here, okay? So we have to evaluate what is this distance. In particular, we can consider this rectangle, okay? Sorry, this triangle that is a rectangular triangle, and we can simplify the situation considering that we want to measure the dimension of the laser. For example, here, let's suppose that this distance is L first, okay? And in particular, what you know that the more general condition when you have a Gaussian beam is that the diameter of the beam is related to the beam waist by this condition. Let's suppose that this is L first and this is the Rayleigh distance, okay? In particular, I never remember this, this quantity Z here is the Rayleigh distance, is the distance by which we have an increase in the radius of the beam by a factor equal to square of 2, okay? And so let's evaluate what is the Rayleigh distance in this case for this in this geometrical condition. Let's see. This is pi W0 squared divided by lambda. Okay, this is the wavelength. And this is a pretty huge Rayleigh distance because this is in the order of millimeters. Okay? Sorry, 100 of millimeters. So now, in your opinion, is it really important to find out what is this distance or not? Since you know that you have to compare this distance with the Rayleigh distance, and you already know that this quantity, so the width, let's say, of the pipe is 10, I can see now. Yes, this is 10 centimeter. I rewrite it here. Okay. Since you have this, L is 100 millimeters, and the Rayleigh distance is higher than L. Okay? Is it really important to find out what is the real value of L first or not? No, that's correct. So because, of course, what we can say, we can say that L first will be more or less equal to L divided by 2. Okay? And so more or less equal to 50 millimeters. What does it mean? That if this quantity is lower of the Rayleigh distance, what we can say that more or less this is equal to W0. Okay? In my opinion, this is a correct way to proceed. Let's see if he says the same thing. Oh, he goes to with the calculation of L first, and in particular, if you want to do the calculation, L first is equal to this quantity, okay? And what you get is, 5.005 centimeter, okay? So as you can see, our approximation is pretty good, okay? So in particular, in this case, and this, what does it mean? That this is a very good, a well-designed LDV, because the dimension of the beam does not change inside the pipe too much. Okay, so this is a good working condition. Okay. Then, okay. Okay, at which distance, one from the other, do we find the two laser spots on the same inner surface of the pipe? So, what is this distance, more or less? Let's call it the spot. Okay? And so what we need to find is, or better, let's say that this spot is equal to what? To 2 times this quantity. And this quantity is half of the width of the pipe multiplied by the tangent of theta. So since we have already defined theta, what we get is, and we can also, of course, say that is more or less equal to L multiplied by the angle itself, because the angle is very little. Okay, so the tangent of theta goes with the angle in this condition, and so we have 3.25 millimeters. Okay. Okay. Now, let's say we have the real question about LDV. Okay. Let's say these are considerations that you can think of when you try to design or to have the idea of how your design will work. Okay. So these are good working conditions. But anyway, now the point is, if the fluid moves at a constant velocity v equal to 8 meters per second, so if we have that v is equal to 8 meters per second, what is the frequency related to this velocity? Of course, what we suppose that if the fluid moves of a certain velocity, all the particle moves together with the fluid. Okay. As I said before, this is quite easy because we know that we have the velocity divided by the fringe's distance. Okay. And in particular, this is equal to 800 kilohertz. 800 kilohertz. Okay? Okay, so another point. When you have an LDV exercise, there is also always, let's say, a theoretical question. Okay? So, review more or less what are the setup, the schematics, and so on. Okay? The photodiode, and so on. Okay? Okay, from the point of view of exercising, more or less, this is all you can find. Probably in some exercise you have a range of velocity, so you have to find what is the minimum and maximum frequency, so something like this, okay? You have, sometimes you have the diameter of the lens and then you have to find the angle, okay? But sometimes you have directly the angle, so, I mean, this is all that you can find, or we will find on laser Doppler velocimeter. Okay. Okay. Now, let's do something about about speckle, let's say, to review what is important to remember. Okay, okay. This exercise in particular was taken from the February the 3rd exam of last year. Or no, this year, 2007. This is your exam. No, this is not because... I don't know. Okay, anyway, this is the date is 2017, but I believe that this... No, okay, this year. Yes, you will have 2018. Okay, sorry. Let's consider this exercise. Let's consider this exercise. So, we have an interferometer that is working in a self-mixing configuration with a Heaney source. So we need Heaney, and we know that we work in a self-mixing configuration. We use a Heaney Zeeman, so this is the setup that we have seen last time. In particular, the power that is emitted by the laser is 1 milliwatt, and we're working on a diffusive target, with a D coefficient that is equal to 1. Okay? Now, the first question is a theoretical one, because I want to know the dynamic range of measurement, or the maximum, let's say, displacement of the target is limited or not in this condition. And of course, the answer is yes. So we have a limited displacement of the object, displacement of the target, in principle, what you know that if you call DLM the maximum displacement of the object, you know that this should be much lower than the longitudinal dimension of the speckle that is overposed to the output mirror of the Heaney laser. Okay? This is the condition. If you say this is quite good, quite enough. If you want to go further, you can say that this condition is due to the fact that we know that the noise equivalent displacement in case of a speckle pattern distribution is more or less proportional to the wavelength and to the ratio of these two quantities. So the more the displacement is close to the longitudinal dimension of the speckle, and the higher the error of the measurement. Okay? Because if this quantity is equal to the longitudinal dimension, we have an error of the wavelength. And this is much more important, if the target moves of a quantity that is higher than the longitudinal dimension of the speckle, we have a phase jump that is completely uncorrelated, because we move from a speckle to the other, okay? And you know that in the space, the speckle represents areas in which the field correlation is higher than 0.5. If you move from a speckle to the other, you have a casual phase jump. Okay, so you cannot do, you have an error on the measurement. Okay? So this is, let's say, the more correct answer to this question. Then, the other point is, you have your laser, and then here you have the diffuser. What is the diameter of this spot onto the diffuser? If you know that this distance Z0 is equal to 40 centimeters, and if you know that you have a beam waste of the output of the Heaney laser of 50 micrometer. Okay? This is easy. We have already seen this calculus during our lecture. What you have to find out is the divergence angle of the Heaney laser. So this is theta. Okay? And you already know that this angle is given by the wavelength divided by pi W0. Okay? Then, once that you have this divergence angle, you can find out the diameter of the spot, of the circular spot on the diffuser, using what? A relation that says that you have 2 times the multiplication of this angle by the distance Z0. And in particular, you have to find out this quantity, and this is equal 3.22 millimeters. Yes, let's say that you always have this condition, okay? The one that we have seen last time, some minutes ago, that it says that the diameter, the radius of the beam is always related to the beam waist by this condition, by this working condition. Okay? This is what we have just seen. Okay? Now, it is good to consider what is the Rayleigh distance in this condition. This is equal, again, pi W0 squared divided by the wavelength. And this is in particular equal to 12.4 millimeters. Okay? So now, since we are considering a distance z that is equal to z0, and z0 is much higher than this distance, we can cancel out the 1, cancel out the square root, and you see that this this quantity is equal to E divided by 2. Okay. Okay. Good. Now, the other point is, what is the transversal dimension of the speckle that is able to be reinjected, let's say, into the laser cavity? So we want to understand now, we have again the Heine laser. Here we have the diffuser. Now I want to understand what is the transversal dimension of the speckle that is reinjected into the Heine laser. Okay? Now, we have seen that with a circular spot onto a diffuser, the dimension of the speckle, the transversal dimension of the speckle, is always related to what? To lambda multiplied by the distance in which you want to evaluate the dimension. So in this particular case, this is again equal to Z0, okay, divided by the diameter of the circular spot. Okay? So, okay, this is Z0. So I have lambda Z0 to theta Z0. Yes. And this is equal to lambda divided lambda pi W0 okay, we have this quantity, this value for the transversal dimension of the speckle here at this point. Another thing that I have said last time is, and it is important, is that if this condition is true, hold, what you can say more or less in a qualitative way that if the target move, the speckle is dragged. Okay? So if the target move, the speckle moves with the target. Only and only if this condition is true. Okay? And this is a very good point, because what we know from this calculation, that this quantity is lower than 2W0. 2W0 is the diameter of the spot on the output mirror. Okay? So just one of the 1,000 of speckles that are emitted or diffused by the diffuser can interact with the Heine laser, or the unperturbed field that is inside the laser. Okay, so this is true. And in particular, if this condition is true, we can measure the displacement of the target, because we will have the speckle that moves in this way, and so the information on the displacement is inside the speckle. Okay? And the error is minimum. Okay? So this is the point. Now, the other question is, the value. The value is 78.5 micrometers. Okay? Now the other question is, what is the ratio between the power that is contained in the speckle and the power that is emitted by the laser? So we can write it here. What is the ratio between the power contained in the speckle and the power that is emitted by the laser? Now, to answer to this question, we have to suppose that all the speckles have the same power, okay? And we can proceed using acceptance and brilliance principle, okay? Because let's suppose that we want just to understand what is the power inside the speckle, okay? What we know? We can evaluate this power using what? The brilliance of the diffuser, because now it's the diffuser that is emitting light. Cesare has told me to tell to you that, of course, brilliance and brightness are the same thing. Okay, I use brilliance because I'm used to say brilliance, but brightness is the same thing. Okay. This is the brightness or brilliance of the diffuser. And then we have to multiply the brilliance of the source by what? By the acceptance of the speckle. Okay? So let's call it the acceptance of the speckle. And in particular, we can write, looking there or looking here, that the acceptance of the speckle is given by what? The area, the transversal area of the speckle, that is given by pi st divided by 2 squared. This is the area of the speckle. Okay? And then we have to multiply it by what? By a solid angle. Now what solid angle? Remember, we are considering the speckle, so we are here, and we look at the diffuser. So the solid angle is this one. This is omega speckle. Okay? And in particular, we can write pi multiplied, for since we have the angle, theta squared. This quantity is the solid angle under which, let's say, the speckle sees the diffuser. Okay? Good. Now, let's see if I have intermediate result. The other point is how we can find the brilliance or the brightness of the diffuser. because of course this is important to know. We know that all of the power of the Heine laser will go onto the diffuser. So the power that is back scattered or back diffused by the diffuser is D multiplied by PL. D is the diffusive coefficient of the diffuser. It is, in this case, is equal to 1, but we always have to remember that. Then what we have to use? We have to divide this power by the area on the diffuser. This is given by pi d squared. This is the area of emission. And we must use the effective solid angle of emission of the diffuser that we have seen last time, or 2 times ago, is equal to pi steradian. Okay? Perfect. We have everything. Okay? So we can put numbers, but anyway, what you will see is that PS became equal to delta D, delta PL, ST squared over 4 multiplied by 1 Z0 squared. Okay? And in particular, okay, this is equal to more or less 10 picowatt, so that the ratio of PS over PL is more or less equal to 10 to minus 8. Is it correct? Because two is sorry, I just look. See, yes, no, it's correct. What is your question?
Saying where did the Z0 come from? Because I have this.
No, this is the, because of course you have also to remember that theta is related to the distance. Sorry. Here you have Z0 because D is equal to 2 theta Z0. So here you find Z0. Okay? You always remember this. Okay. Okay. Now, this is more or less the same question of the first one, because from the data that you have, for all the quantity that you have, is it possible to estimate what is the maximum dynamic range of displacement? Of course, the answer is yes, and we just need to find out what is the longitudinal dimension of the speckle. And in particular, this is always equal to, again, we are here, we are looking at the longitudinal dimension here of the speckle, and this is again the wavelength multiplied by 2 times, this time, the distance Z0 divided by the diameter, and this quantity is squared. In particular, we have 39 millimeter. Okay. So we can also look at this information in a good way, because of course we know that we must limit the dynamic range to a quantity that is much lower of this quantity. But since now we are using the interferometer like a vibrometer, we are measuring vibration, of target, vibration are usual, let's say, 100 of microns, some millimeters. Okay, this is 39 millimeters. It is good. It's not bad. Okay, because this quantity is definitely larger than some millimeters of vibration. Okay. So you don't have to think that if we have to limit the displacement, this is a bad thing, because the maximum displacement is usually large. Okay. Okay. Okay, now there is another point. This is more related to the noise equivalent displacement related to the quantum noise, because the exercise says, now, let's suppose that we don't use a diffuser, but here we use a corner cube. Okay? The corner cube can move. So in such a way we are not any more limited by the spectral pattern distribution. But the point is another one. We want to evaluate now what is the new power that is sent back to the Heine laser in this case. So let's cancel out this and also this. In a way, what we have is that we still have emission under the angle theta, of course. Then we have total reflection. And so, more or less, this is the diameter of the spot related to the fact that now we are using a corner cube. Okay. Okay. Another question is, what is the new ratio? Because this was the first one. So in a spectral pattern distribution condition, so with a diffuser, we have that the power that is back injected into the Heine laser is very low, 10 picowatt, starting of course from 1 milliwatt. Then the question is, now what is the new ratio? Since now we are using a corner cube. This is more easier if you want to say you have already seen this when you have evaluated the power budget of a telemeter with the cooperative target. Okay, because this is simply given by what? By the ratio of the power in the, let's say, the output dimension of the laser. So this is pi multiplied by 0.02 divided by what? By pi dc divided by 2 squared. Okay? And in particular, let's say that dc, this diameter, is equal to what? To 2 times, let's say, the diameter of the spot onto the target, onto the corner cube, that was equal to 2 times 2 theta z0. Okay? So this is 4 theta z0. Okay, this ratio is, in particular, okay, I evaluated this. This is equal to 6.44 millimeter, and this ratio is close to 2.4 10 to minus 4. Okay. And now if you want to evaluate what is the absolute value of the power when you use the corner cube, this is equal to 0.24 microwatt. Okay? So we have a huge change in power, because now the power that is able, let's say, to do the interferometric measurement is 0.24 microwatt. Before, with the diffuser, it was 10 picowatt. Okay, we have a huge increase in usable power, okay, for the measurement. And where you find, what is the translation of this huge increase, in the power that is usable? Well, you find out into the NED, the noise equivalent displacement, the noise equivalent displacement related to the quantum noise. Because in particular, what you know is that, so we review also another definition of the noise equivalent displacement related to the quantum noise, is we have used more frequently the relation that says that the noise equivalent displacement is proportional to bandwidth and photodetected mean current. But we can of course use the one that says that you have, okay, lambda 2 pi d multiplied by okay. Yes, okay. H mi b divided by 2 eta p. This is the Planck constant. This is the frequency of the laser. Okay. This is the electrical bandwidth. This is the quantum efficiency of the photodetector. And of course, this is the mean power that you are using, okay? And this is the fringes visibility, okay? Now, the exercise says, let's use a quantum efficiency equal to 1, let's use a fringes visibility equal to 1, and electronic bandwidth equal to 100 Hertz, and that's all, okay. And as a note, it says also that the Planck constant is equal to 6.62 10 to minus 34. Yes, this is true. Okay, so you have not to remember this quantity, okay?
This is the first one you said for the quantum noise.
Sorry.
Bandwidth and relation of bandwidth and mean current. What is the first, there are two equations of energy.
Yes, of course. This is, you can, with this one, if you remember that, you always have that when you look at the photodetector or photoreceiver, the spectral responsivity of the photoreceiver can be written in this way. So this is the quantum efficiency related to E, where E is the electron charge, divided by the photon energy. So again, the Planck constant and the frequency, okay? So if you insert this here, you find out the other question, because of course you know that it's 0, or E is always related to sigma multiplied by p. Okay? So you can go back to the other relation. Okay? And now we can answer to the question. It seems a lot of calculation, but they are not. If you stay quiet on your desk, this is an easy exercise. Because, okay, this is our relation, the noise equivalent displacement in the quantum regime of detection. These are quantities that are written in the exercise, okay, so you don't have to make a hypothesis, okay, and we can find out what is the noise equivalent displacement when we work with a speckle pattern distribution. So what does it mean? That we have to use that P is equal to the power related to the speckle, okay, and here we find okay, sorry. Okay, we have 129 picometer. Let's say not bad. This is a very good resolution, especially if we think of all that is happening, because we have a single spatial mode radiation that is going onto the diffuser. Now the back diffuse light is multimode, but many multimode. We have thousands of speckles. Just one of them is able to do the interferometric measurement. The power, let's say, related with this speckle is only 10 picowatt, starting with a milliwatt. But anyway, we are able to do the measurement with let's say, very huge resolution, very high resolution, okay? But what is the increase in resolution if we work with a corner cube? So when P is equal to PCC, and we have a terrific increase of more than 2 decades, because now the resolution is more or less equal to 800 femtometer, okay? So 10 to minus 15, okay? So we can go very, very down in resolution, of course, if we increase the power.
Excuse me, do you mind explaining how did we get the PCC?
Ah, yes. Is exactly what happened in the telemeter, okay? So you have, let's say, this is the big spot that is back reflected from the corner cube. So this is the let's say, the power that is emitted by the laser is now contained in a spot with a diameter that it is given by DCC, but is at these sides, okay? So all the power that can re-enter the cavity is just the power that fall inside the area or the output area of the mirror, okay? So of all this power, just, okay, you are right. Now I'm using, okay, this is what I have to write. This is the optical axis, and this is W0, okay? So, of all this light, just the quantity that is able to re-enter the laser is able to do the measurement, okay? So, to find out what is the ratio of power, it's just sufficient to do the ratio between the areas
So we
of the
have
spot.
W0 squared.
W0 squared. Okay, that's good. Yes, you're right. Okay, sorry. Okay. And okay, maybe in the last minutes we can review also another point that we have seen during our lecture. And the other point is, now, let's suppose that it's not important to consider the diffuser or the corner cube. Let's suppose that the target now is moving in this direction. So let's say this is the velocity or the displacement of our real target. And so we have an angle alpha with respect to the optical axis. Okay? What we know, or what we have seen, is that what you are able to measure with an interferometer is only the component of the real displacement along the optical axis. Okay? So, you are able, to measure only this quantity. Let's call it DRM star. Okay? This is important. So now, you have, of course, an error on the measurement. And the error, what is the error? Because you can write it E. E is given by, let's consider just the modulus of this two vector, okay? And dLm, this is the real measurement, okay? Minus dLm star, and in particular this is equal to dLm minus dLm cos of alpha. Okay? When you have, let's say, a cosine error, so when the target moves not along the optical axis of the system but with an angle, you always underestimate the real displacement. Okay? And so that we can write dLm multiplied by 1 minus cos alpha. Okay? Good. Now, the exercise asks you to find out a maximum angle alpha